Hello, everybody, dear colleagues. Good morning, good afternoon, good evening, good night. Let's start our first seminar in May. And our first speaker in this month is, it's a pleasure for me to present Natasha Rozhkovskaya from Natasha, what university?
Kansas State University.
From Kansas State University, yes. She will speak on generating functions of polynomial tau functions of soliton hierarchy. Please, Natasha, you can start.
First of all, I would like to thank you very much for invitation to speak at this seminar. I think it's great series. I enjoyed many talks during the year. And I would like to thank organizers for keeping this running, because it's a great opportunity for all of us to find out what our friends in different corners of the world are doing right now. So thank you very much. It is really great. Please continue doing this for us. And today I would like to talk about part of representation theory, which is inspired by solitons, soliton hierarchies. And the amazing feature of this part of mathematics, that it is at the crossroad of many areas of mathematics. And that means that mathematicians from different areas are involved in research which is related to soliton hierarchies. And also that means that we may speak different languages, because we may be from algebraic geometry, from integrable hierarchies, we can be from representation theory, from partial differential equations. And the first thing that I would like to do today is to give some overview, to try to explain what are the questions that we consider, and also to point out what kind of dialect, what kind of language I speak. And just going ahead a little bit, it's going to be here on this island. It's representation theory related to symmetric functions. So my main language is symmetric functions. And this diagram is a diagram of different interpretations of Kademtsev-Petviashvily hierarchy. And I would like first to go over different transitions here and different interpretations, a little bit to give overview, like how people approach this. So what kind of question inspire people and how they try to solve them. And also I would like to say that this is only part of a much bigger diagram. For example, one could go in this direction, which I did not include here, to consider Luck's form of Kac hierarchy. So I did not include it because I already have a lot of transitions here that is already overwhelming. And also because we are not going to talk about Luck's presentation of Kac hierarchy today. So my first goal is just to try to convince you that what I'm going to talk about is interesting because it's related to different part of mathematics. And the first thing that I would like to mention is that everything started with some partial differential equations, nonlinear partial differential equations. And this is one of the examples of such equations. This is called KP equation, Kademtsev-Petviashvily equation. It is on a function in 3 variables, tx, y. And you can see that it is a nonlinear partial differential equation. And as we know, it is not easy to solve partial differential equations, nonlinear partial differential equations. There are not so many that we can solve. And this one and few other ones are remarkable in the sense that not only there are explicit solutions, but also one can write them in very reasonable formulas. These formulas contain exponential functions, so formulas are you can work with them. And moreover, among solutions of this partial differential equation, there are functions, wave functions, which behave in very interesting way. More precisely, they look like, so they are called solitons. So what does mean a soliton? So this is something like a wave function, so something that behaves like a wave. It preserves its shape with the time. And the most interesting feature of solitons is that when two solitons meet, when they collide, they do not destroy each other, as it often happens with these kind of functions, with these kind of solutions. But they interact in some interesting way, and then they just go in their own directions, like as if they did not meet at all. So very strange and very unusual behavior for the solutions of nonlinear partial differential equations. And it is so unusual that when solitons were first discovered experimentally, mathematicians didn't believe in that. They said, okay, so that's not possible, that cannot be like that. And only later they realized that there are actually equations that can describe such kind of waves. And the question that arose very soon after several equations of this type were described was, what does make soliton equation to be a soliton equation? So when do you have solutions of this interesting kind? And after decades of research, it turned out that the answer to this question is in the hidden symmetries of these kind of equations. And these hidden symmetries very often are described in the language of completely different part of mathematics. For example, algebraic geometry or representation theory. And this is the direction which I would like to take today. So we start with just one equation, and we say that people got excited about this equation because it was very unusual. And then the question is, why this equation is so unusual, how we can produce other ones, and how we can solve them. So these are like the main questions. And the first point that we have to make here is that this KP equation turned out to be not just an equation on its own, not living its own life, but a part of big family, countable family of other nonlinear partial differential equations, which is called KP hierarchy. And this KP hierarchy is integrable in the sense that you can find common solutions to all these equations, which is also quite unusual. Okay, so let's go and look to another transition. And the next transition takes our problem in partial differential equations and transforms it into a problem in algebra. So I know that letters are very small here. I hope that later it will be somewhere, it will be written in bigger letters. So what happens here? It turned out that all these equations of this KP hierarchy, they can be written in the form, in very special form. So not every nonlinear partial differential equation can be written in this form, but these ones can. So using Hirota derivatives. So Hirota derivative is quite unusual operation. You have a polynomial, you have two functions, and then out of this polynomial you construct differential operator, do something like this, and then as a result you get a new function. So it is some kind of operator. And here KP equation in terms of Hirota derivative starts to have this form. So it corresponds to this kind of polynomial applied to the same function. And this allows to transform problem in partial differential equations into algebraic problem. And then it's sort of easier to work with this kind of problem. And then if you find, so now instead of this system, we have a system of bilinear system of equations that are more algebraic. We are looking for the solutions in the polynomial ring of infinitely many variables, which we are going to denote as P1, P2, and so on, or in the completion of this ring. So the solutions of this system, of bilinear system, or other interpretations, which we will consider later, are called tau functions. Tau function is synonym that it is solution of this bilinear system. And if it is polynomial, we will call it polynomial tau function. And if it is in completion, then it is not polynomial. So our goal today will be to describe polynomial tau functions of this bilinear system that corresponds to KP hierarchy. And whenever we find the solution here, we can make change of variables back. For example, for this equation, we can make this change of variable from tau function, construct a solution of the initial partial differential equation of KP equation. So now we are on the territory of algebra. So we came to the algebra. So now, what is the meaning of this system? So the meaning of the system is quite deep, and it explains why we have so many symmetries here, but we still have to make several transitions. So the next transition that we want to make is to explain that actually all this countable system of some kind of algebraic equations can be written in very compact form as just one identity, one equation. So here we have some expression which is formal series in variables y's, like y1, y2, y3. And if we consider the Leur decomposition of this equation and look at the coefficients, then we get all these equations in this system. So the whole KP hierarchy can be written as just one bilinear identity. We just have to understand what is this. And so far we still live in polynomials in these variables. So how we can find, so what is this? What is the meaning of this Py, and how we can find solutions of this identity? So here we come to the crossroad where we have three interpretations. And usually when people try to answer different questions in this area, they just use these interpretations, interplay between them. So we use all these three interpretations. So far we had bilinear identity, so this kind of condition, in the polynomial algebra. So this is that case. Now we are going to consider other kind of spaces and equivalent conditions there. So I will spend some time explaining some notations here on the next few slides, but let us see what we have in general here. First of all, this bilinear identity in polynomial algebra can be written as bilinear identity, so some kind of condition, in another space, which is called the fermionic Fock space, or it is semi-infinite wedge product of countable dimensional vector space, so something like that. So the explicit definition I also want to give a little bit later, just in a couple of slides. And there is a statement that tells that there are relations between polynomial algebras and these exterior kind of algebras, which is called boson-fermion correspondence. And on the level of vector spaces, it sounds like this. So just a copy of polynomial algebra is not enough, it's small. But we can take countably many copies of those and label them by integer numbers. And these labels we encode in one more variable z. So here we have graded components, each of them is just a polynomial algebra. So now we take all this graded space labeled by integer numbers, and then this is isomorphic to this semi-infinite wedge product of certain vector space. So commutative is isomorphic to anti-commutative. As vector spaces, there is nothing, I mean, that's not just isomorphism of vector spaces, because as vector spaces, this is countable dimensional, this is countable dimensional, that's not like a big deal. But this is isomorphism of models of certain algebraic structures. And these algebraic structures are infinite Clifford algebra or algebra fermions, which will appear later, or Heisenberg algebra, or Lie algebra GL infinity. So they are isomorphic as models over certain algebraic structures, and that allows to use this isomorphism to transport back and forth different things. So this boson-fermion correspondence allows to rewrite this bilinear identity as a bilinear identity in this vector space. And another interpretation where we are going to use our tools, so like this is the place where we do all the work, is to interpret that space of polynomials as a ring of symmetric functions. So symmetric functions are polynomial functions which are invariant if you permute the variables. And it is well known that it is a polynomial ring. You can express any symmetric function as a polynomial of power sums. So using this identification, we can also think about this bilinear identity as some condition on symmetric functions and try to solve it here. And this is what we are going to do. We will try to solve it here, and then we can use these transitions to go to other places. Okay, so So that's about vector spaces where we go. And what is this? What is this identity? I will give more details just in a couple of minutes. And before I go to more details about notions which were mentioned on the previous slide, I would like to mention one more interpretation which explains the symmetries behind all this KP hierarchy. So what is the deep meaning? So now, if we consider this bilinear identity in exterior semi-infinite exterior wedge product of the space V, it turns out that this condition that we have here is equivalent to the condition that our element tau, our tau function, lives in the orbit of vacuum vector of the action of the group GL infinity in that space. So we, by this bilinear identity, KP hierarchy corresponds to an orbit of vacuum vector of GL infinity. So we are not going to use this late in presentation, it's just a remark, but this is part of some proofs of some statements which will appear later. Okay, so next I just want to give a little bit more details on this space. What is this exactly? So in one of these interpretations, and then we will look at bilinear identities themselves. So how this space is defined? Let's take a vector space which has countable dimension, and let us consider the basis of this vector space. And we will construct monomials with the help of these basis vectors. For example, we are going to call this kind of monomial, which is infinite in one direction, M vacuum vector, and it starts Vm, Vm minus 1, so it goes down consecutively. And then we do the following. So let us take this semi-infinite monomial and let us change vectors in finitely many places. Let's change few of them, but the rest stays the same. So only finitely of them can be changed. So we will get this kind of monomials. These are allowed kind of monomials. And we are allowed to take linear spans of these kind of monomials, which are different from the vacuum vector only at finite number of places. And the linear span we're going to denote like this. And this is going to be one of the graded components of this space, which we call fermionic Fock space or semi-infinite wedge product of the space V. So I would like to pay attention that this is infinite, but it is infinite in very controllable way. So it is actually locally, it's finite. Locally, we have only finite things here. So infinity here is very much restricted. So this is our space, one of the spaces where we have bilinear KP identity. And now this is the identity itself. So we look at the elements in this fermionic Fock space, and we impose some condition. I would like to explain what is this condition. This is the action of certain operators, which we are going to call charge-free fermions on that space. So another name for this is Clifford algebra, infinite dimensional Clifford algebra. It has generators psi plus minus labeled by integers with this kind of relations. And in our story, we will often combine generators of this kind into generating functions or formal distributions. So in this case, they are even quantum fields. So we will just basically work with the generating functions. And then these two relations, in terms of generating functions, become these kind of relations on formal distributions. And here, delta of uv is a formal distribution which is defined this way. K goes over all integer numbers, and it has properties similar to properties delta function. So it's formal delta function. And what is the action? So what is the action of these operators on that space? It is very natural. So they naturally act on that space. In some sense, they are like creation and contraction operators. So if you take psi plus k and act by it on the monomial, which lives in this space, that is just the same as to attach to that monomial in front the vector with the corresponding index. Okay, so you just write down one more basis vector in front of this monomial. So it's sort of it's a creation operator. And what does this operator do? It looks like a complicated formula, but actually it's just a long way to explain a very simple thing. This operator goes to the first vector and checks, is it the vector the same as this vector, or like this stuff? If it is the same, it contracts with it, and the leftover is the result of application. If it is not the same as v minus k plus 1/2, it goes to the next one and checks that one and contracts if they coincide. If not, then they go to the next one. And you keep going, and you scan all the elements of this monomial. So there, it's infinite. And even for the sum here is infinite, the result is going to be at most one monomial. It can be 0 or just one monomial. So this is the action of Clifford algebra or charge-free fermions on that space. And that allows us to write down this condition. And we are interested in elements of that space which satisfy this condition. Okay, and the second interpretation, the island where we have symmetric functions. So what do we have there? So here we will need to introduce few notations, and I will do it on the next slide and the ones which are later. But let me just go ahead and a little bit explain, like show you what we will get in the end. So ring of symmetric functions is just ring of symmetric functions. Again, one copy will not be enough. It's just one polynomial algebra. We have to take countably many of them and combine in one big boson-Fock space. Okay, so it's just many copies of polynomial algebra, many copies of the ring of symmetric functions. And then we will describe the action of Clifford algebra of charge-free fermions on that space using these generating functions. And I have to explain what is H, E orthogonal, E, H orthogonal adjoint. So this I'm going to explain just in a minute. And we will also show examples of tau functions. We will show solutions of bilinear KP identity in terms of symmetric functions. So we will provide the answer to the question, what are solutions, polynomial solutions of bilinear KP identity in the language of symmetric functions. So to explain that formula for formal distributions for psi plus and psi minus in the language of symmetric functions, I need some notation. So let us review some notions from the ring of symmetric functions. So we're going to consider functions which are symmetric with respect to variables x's. So these are going to be always variables where we have invariance with respect to permutations. Then, very important for us examples of symmetric functions are complete symmetric functions, these ones. So this is a definition. And this is a baby example of one of them. And elementary symmetric functions. The difference in the definition is that here we allow repetitions and here we don't allow repetitions. And this is another baby example of elementary symmetric function. We will also need power sums, which are just power sums. This is the definition, and this is an example. And we will need sure symmetric functions, the famous symmetric functions, which are characters of irreducible representations of JLN. So whenever lambda is a partition, and if we take enough variables x's, then sure symmetric function can be defined by this formula. And then we have the following kind of information which is very useful for us. So first of all, for our story, it's remarkable and it's convenient that the ring of symmetric functions is a polynomial ring. And we can write down it as a polynomial ring in variables which are complete symmetric functions, or elementary symmetric functions, or power sums. So whatever is convenient for us. And sure symmetric functions, which form a linear basis of the ring of symmetric functions, they actually can be written, of course, in these variables. And this is how it is usually done. So this is definition as symmetric polynomial of sure symmetric function. There is a formula which is called Jacobi-Trudi identity, which expresses sure symmetric function through complete symmetric functions using determinant. And now we can plug in power sums into these guys, and then we get this as a polynomial in power sums. And remarkable theory by Sato from 1981 that these polynomials that we obtain in the end, they are examples of Kp tau functions. They satisfy this bilinear identity. And therefore, if we go back, they produce some solutions of those of the Kp hierarchy. Okay, and but I did not explain yet how these guys act on the ring of symmetric functions, and this is what I want to explain because this is important for more general statement which we want to formulate quite soon. And to explain the action of Clifford algebra or the algebra of charge theory fermions on the ring of symmetric functions, we need to introduce scalar product on the ring of symmetric functions, which is just a natural one where sure symmetric functions form orthonormal basis. And then for any operator acting on this space, for example, for multiplication by another symmetric function, we can define a joint operator as we usually do and consider joint operators. And for example, it is known that for a joint for multiplication by power sums is nothing else but normalized differentiation by power sums. And using operators of multiplication and adjoint operators, we create several formal distributions, so we can call them generating functions, so they're actually quantum fields acting on this space, which we define in this natural way. So we combine in one generating function all complete symmetric functions, multiplication by them, all elementary symmetric functions, the adjoint operators of these ones, and the joint operators of these ones. So these are our main building blocks which allow us to do a lot of things. So these are the main tools that are used in construction of tau functions, which I will mention very soon. And if we rewrite all these series, all these formal distributions in terms of power sums, we would get these kind of expressions. And those of us who have seen vertex operators presentations of Clifford algebra, you can recognize that these are building blocks that enter into this vertex operator presentation. So this is the same thing. We just use different kind of generators because it's simpler and it's easier. It's just less technical. And those formal distributions, those quantum fields that we constructed, they have very nice commutation relations of this kind. And this lemma is more or less the main instrument for the proof of many statements about construction of polynomial tau functions, which I say later. And it is an exercise in McDonald book on symmetric functions. So it can be found there. Now, let me just now mention what is the action of fermions of psi plus and psi minus on the ring of symmetric functions. So this is our ring of symmetric functions. This is many copies of that because one is not enough. And the coefficients of these two formal distributions, psi plus and psi minus, they act on this space. And the action is described by these two formulas. So first we apply adjoint operators to EKs. Then we apply multiplications by complete symmetric functions. And it turns out that if we define these two formal distributions by these formulas, they will satisfy the commutation relations of charged free fermions of Clifford algebra. So this also follows from that lemma. It's very easy computation. And we have a situation, a picture which is dear to the heart of any person who does representation theory, because we can start with a vacuum vector. In that case, it is just a constant symmetric function, which is 1. Apply a bunch of these creation operators with appropriate indices, and we get all these basis elements. We get all sure symmetric functions here, and just we also know that they are going to be solutions of some identity. Moreover, there is something that can be called generating function for all sure symmetric functions. And it is also related to all this picture. Namely, let us take again this constant symmetric function, just one, and apply these quantum fields psi plus u with different variables to this one. The result will be some formal distributions. Those coefficients will be symmetric functions. And again, using that lemma, it's very easy to find out what is going to be the exact formula of this formal distribution. This is how it looks like. We have a product of generating functions for complete symmetric functions and some factors of this kind. So let us take this formal distribution and expand it in powers of u. We will get here some coefficients, q lambdas. So lambda can be any integer vector. So sometimes we will have 0 here, sometimes we will have some symmetric functions. But whenever lambda is a partition, the corresponding coefficient is going to be sure symmetric function. In that sense, this expression is the generating function for sure symmetric functions, because all sure symmetric functions appear here as coefficients. So there is something else when lambda is not a partition, but whenever it is a partition, we got our sure symmetric functions. And here is the summary of the statements that we made so far. So sure symmetric functions are polynomial solutions of Kp bilinear identities. They are also coefficients of certain generating function. And this generating function is the result of application of quantum fields, charged free fermions, to a vacuum vector. So we want to use all these ideas and expand them to construct other, and actually we will be able to construct all polynomial solutions of Kp bilinear identity. And also to try these techniques in other cases. And this was successful in BKP case and also multi-component Kp case. So, and before I describe that construction, I would like to show you the result, the first result, how all polynomial tau functions were described by Victor Kac and Johan van der Leur in their paper in 2018. So here how we can get all solutions of Kp bilinear identity. And from this result and from the result which we will formulate a little bit later, we will see that actually there is not much freedom. So all polynomial tau functions, they look more or less the same. So what happens here? Let us take sure symmetric functions as lambdas and recall Jacobi-Trudy identity and express through polynomials, as we already did a few slides ago. Now let us take these variables and shift them by complex numbers. Let's shift each variable in this determinant by a complex number. So we have a collection of complex numbers here. The resulting determinant is going to be, of course, a polynomial in power sums. And it turns out that it is going to be a tau function, Kp tau function. And any polynomial tau function that you will create will be of this form for appropriate shifts. So all polynomial tau functions have this form. So this is one way to describe all polynomial tau functions. And the next one will involve components which are closely related, which remember about the action of charged free fermions. And it is based on generating functions for polynomial tau functions. Okay. So here how we go. So another way to construct all polynomial tau functions, all solutions of Kp equation. So let us go back and let us take our generating function for sure symmetric functions. So this, when we expand, we get here sure symmetric functions in the general sense. Let us take a collection of complex valued Laurent series. Let us fix as many as there are variables in this formal distributions. Let us take our generating function, this one, and multiply by all these Laurent series. So sort of twist. We get a new formal distribution. So let us expand this formal distribution and look at these coefficients T lambdas. So we're interested in these T lambdas. And here are the statements about the coefficients of this slightly changed generating function. So first of all of these coefficients are going to be solutions of Kp bilinear identity. They are going to be polynomial tau functions. The second statement is that any polynomial tau function, if you've got a polynomial tau function, is going to be of this form, meaning that you show me a polynomial tau function, I will think a little bit, and I will find a Laurent series that I can insert into this formula, expand, and your tau function will be here, one of these coefficients. Moreover, this generating function which we wrote down, it's a determinant of smaller generating functions. And each coefficient, each polynomial tau function is also a determinant type, has determinant type formula. So all polynomial tau functions have this form. So this is the statement. Okay, so now all these ideas can be expanded in some other cases. And I would like also quickly, without many details, tell what is going on in BKP hierarchy. So B stands for type B. So if KP is for type A Lie algebras, because it's GLN type or GL infinity type, B is orthogonal type. So it's that's the meaning. And there is also an equation which is analog of KP equation. It's called BKP equation. I think I never saw it in the form of partial differential equations, but in terms of Hirota derivatives, this is how it looks like, the algebraic formula of that BKP equation. And again, this is not just equation on its own, it's part of big countable system of equations. And this big countable system of equations corresponds to one bilinear identity, which has a meaning in representation theory. Now here, these guys are called neutral fermions. And what are they? We will see on the next slide. And tau are also polynomials, but in slightly different space. So they are living in slightly different space. So let us explain a little bit more on the details that we have here. So neutral fermions, what are they? So or type B Clifford algebra. Here we have generators only of one kind. They're also labeled by integers, and this is the commutation relation which we have here. And again, our idea is to combine everything in generating functions or formal distributions, and we combine them, and then this relation corresponds to the relation on this formal distribution on this quantum field of neutral fermions. So this is the corresponding relation here. Now, we have to take a smaller Poisson-Fock space. First of all, it's just one copy of polynomial algebra. We don't need many of them, so there is just one graded component. And also, it should be generated only by odd power sums. So P1, P3, P5. So this is our new polynomial algebra where we want to live. And still, this is part of the ring of symmetric functions. And that means that we still can use all our knowledge about symmetric functions to work in this case. We just have to give new interpretations and new things. In particular, in KP case, the important role was played by complete symmetric functions. The analog here is this new series. When it's expanded, we have here coefficients which are called basic sure Q functions. So these will be our main building blocks in this situation. And it can be proved that it lives in our Poisson-Fock space. And moreover, if we take odd ones, they are going to be independent and they generate our Poisson-Fock space as a polynomial algebra. So that's convenient because we have another set of generators here as well. And to explain how we are going to act with our new algebraic structure, neutral fermions, on our new space, we don't have to introduce any new notations or do some crazy things, because we already have our building blocks here. they take exactly the same building blocks as before, multiplication by these complete symmetric functions, elementary symmetric functions, adjoint operators, and we just restrict them on our space here. And this is, we will, if we check, we will see that the commutation relations will be exactly the ones which we want. And here, we do the same thing as before. We take vacuum vector, just one, and apply a bunch of these quantum fields to this vacuum vector. Then we get some formal distribution, which has coefficients in this space, or again, they are symmetric functions. And the formula for this new formal distribution, for this generating function of something, is also not very difficult. So here we're going to have these basic generating functions for QKs. And here we have some factors. Now they're not going to be, so here we must be careful because we have to consider the appropriate expansions of this rational function. So it looks like very technical, but it just says that we must be careful where we live, in what, where we take these expansions of this rational function. So this is our analog of the previous generating function for sure symmetric functions. And here, if we expand this one in powers of u, we also get something remarkable. When lambda is a strict partition in this sum, we get something which is called sure Q functions, which also appear quite often in representation theory. And there is a statement which is proved by Yo, that not only we have here this remarkable, well-known in representation theory creatures, but also they give us examples of solutions of BKP bilinear identity. So they are tau functions in this case, in type B case. And I would like to make here a remark that actually it's quite common, as people understand now, that important examples of symmetric functions are related to these kind of hierarchies. And just to support this statement with one more example, I would like to mention multi-parameter sure Q functions because it was of some interest for myself. Basically, you have to take definition of sure Q functions and in some points substitute powers of x by shifted powers of x, shifted by sequence, some sequence of complex numbers. So these objects were introduced combinatorially by Vladimir Ivanov in this year, and also some combinatorial properties are studied in this paper. And here are examples of applications of these objects. They appeared quite recently as eigenvalues of Capelli polynomials of certain Lie super algebras. They also generators for equivariant quantum cohomology rings. And it turns out they are also solutions, the examples of solutions of BKP hierarchy. So they also solve BKP hierarchy. So it's just one more statement that this theory is related to many other statements in some incredible way. And we want again to explain what are all polynomial BKP tau functions, how they look like. And we do again this in terms of coefficients of generating functions. And the idea is exactly the same. We take our generating function for sure Q functions and twist it by multiplying by, now in this case, Laurent polynomials. And then we look at this new series and expand it in powers of u. And here we get some coefficients. Then I need to introduce some technical notations, which I'm going just to skip. So there are some delicate issues with antisymmetry because we are going to take fermions, and here we must be careful with definitions. So I'm not going to explain what is written on this slide. It's just explicit definitions that are used on the next slide. But the main idea is contained in these statements. Those coefficients which we saw on the previous, on the couple slides ago, they again polynomial tau functions of BKP hierarchy. And as it is promised, they are going to be solutions so all solutions, so all tau functions of BKP hierarchy can be written in this form. You can construct generating function where you will get it as a coefficient. All polynomial tau solutions will look like fermions. You just have to choose the appropriate thing to insert in this fermion. And the generating functions themselves, they are also fermion. You just have to put appropriate, like smaller generating functions inside this matrix. So in BKP case, we have exactly the same kind of description of polynomial tau functions as in KP case. And one more remark here is that similar statements were proved by us for multi-component KP hierarchy. So it's more general case than just KP hierarchy. I just don't want to go into same kind of notations, but idea is very similar. And I would like to conclude my talk going back to this diagram, just to go back and explain, just to summarize what was the story. So what did I try to say? So our inspiration was in solving some nonlinear partial differential equations. But I'm not a specialist in it, and I have very limited idea how to solve partial differential equations in general at all. So I know only basics which were taught in at the university level. However, it turned out that this problem can be transformed into a completely different area of representation theory, where we have action of Clifford algebra on different spaces. So Clifford algebra acts on different spaces. And in particular, we can act on the ring of symmetric functions. And we can answer to this question in terms of symmetric functions. And then, I don't know if anybody ever does this, but we can go back by all these bridges and get back here, and maybe, I mean, we find the solution that we need here. So, of course, some solutions explicitly were constructed this way, but I just don't know how many people are interested in going back in these transitions. Okay, so that's all that I wanted to share with you today. And the last picture is the photograph of our local artist photograph, so from Kansas. Okay, so thank you very much.
Okay, let us thank Natasha. Any questions, comments? Natasha, when this KP equation was discovered?
I think in so the KP itself, I think in the 60s, but solitons were in 1960s. But equations of the soliton equations in the late 19th century. Like the first was KdV equation, KdV and Brucinet. Yeah. Mm-hmm. So these were the first ones. Mm-hmm.
And when this first algebraic moved to...
It's in 1980s. It's Kyoto school, like Sato and all other things. So it's 1980s. Mm-hmm.
About 40 years, yeah?
Yes, yeah.
Mm-hmm. Maybe Hirota, studying from Hirota.
Yes. So when did Hirota leave? I'm not sure. So I know that this...
In the 70s.
In 70s, yeah. Yeah,
Something
so
like
but
75 or 76.
Yes, but this interpretation for like in representation kind of stuff, it was in 80s. Yeah, so Hirota probably in algebra. Yes, you're right.
More question? So this using symmetric functions, some solutions can be found, but about all solutions, it's...
I don't think anybody knows all solutions. So people look for very interesting families. For example, yeah. So for different kind of so for example, the solutions which we described, they are not soliton solutions. They are not solitons. These are some kind of solutions, but yeah. So there are other methods also. Yeah.
And some, well, not mathematical, but dilettante questions. Tsunami is not a soliton, or?
No, I don't think so. No.
It's different thing.
No.
And for instance, if I don't know that sometimes in some laboratories, physicists or so engineers can do some kind of model of solitons or tsunami. If, for instance, they know formula of solution, can they create a soliton corresponding to this?
That's interesting. I actually asked people myself this question because on YouTube you can find beautiful pictures of some like in channel, like usually they're KDV solutions, but so nobody, I didn't ever meet any experimental physicists who would say yes, we do this. I mean, so
but virtually it's possible, yes.
So there are, on YouTube, there are beautiful videos of KDV solitons. Like there is one very famous one where there are two solitons. There is dramatic music. They collide and go in different directions. So there is one. Yeah. So it's.
Well, we have solitons every day. There's a river here. I mean, the river that goes to the ocean. And when they meet, once a day we have solitons.
Oh, okay. Good.
They're quite nice. So you're welcome.
Okay. Okay. Yeah. Yeah.
And Natasha, I wanted to ask, did you get that buffalo in your backyard?
No, I got rabbits, a squirrel, one fox, and two hawks living up there. So no buffalo yet.
So you've never seen it in the vicinity.
No, we have here Konza Reserve. There are buffaloes there. They are part of scientific experiments, so they are scientific buffaloes, and that's one of them. That's a scientific buffalo. So he serves science.
Mm-hmm. And you mentioned that the solutions you get are not solitons, right?
They are not solitons. No, they are just some solutions. Yeah.
And you cannot get by this way the solitons.
You can. You just. It's just you have to do something different with these vertex operators. No, you can describe solitons in terms of vertex operators. It's just not part of this little story which I told today.
Okay. Thank you.
Okay, more questions? Comments?
If your solutions are not solitons, maybe they have some other meaning.
You mean, so it depends on the meaning of the word meaning. Because for me, if I see something that looks like sure symmetric functions, for me it's already like I'm already excited about this. So for me it's already a lot. For physicists, probably a lot of these solutions, they don't make sense because maybe they sort of don't exist in the real world. I don't know. So since I never made all these transitions back for sure symmetric functions in general, I don't know whether they have physical meaning. So I just don't know this. Yeah.
Okay. More questions? Comments? Okay, no questions, comments. Thanks, Natasha, again for very, very interesting, fascinating.
Thank you very much.
Спасибо, Наташа.
Спасибо вам. Thank you.
У нас в свое время там был профессор в Софии, дитя русских иммигрантов. И когда его спрашивали, где вы собираетесь применить ваши результаты, он сказал, к папке, к профессуре.
Понятно. Ну да.
Еще на факультете висело объявление, Маркс видел проблемы там, где другие видели решения. Это висело лет до перемен, все время на факультете такое было.
Интересно.
Okay, now, just a moment, I cannot find announcement for the next, seminar. Lucia, can you help me?
Там написано TBA.
Who is the speaker?
Alistair. I believe it's Alistair.
Alistair from Canada. And we still have no title.
We have, I believe. Let me just check. The fine Hecke algebras and the elliptic whole algebra.
Okay. Can you repeat once more for?
Affine Hecke algebras and the elliptic whole algebra.
Okay, so this we will have the next Thursday. So see you on the next Thursday in this talk. And now, thank everybody participants for this talk. Спасибо большое, Наташа, еще раз.
Спасибо вам большое.
Наташа?
Да, привет.
Да, привет.
Till the next Thursday.